Hello. So we had learned about central orbits and central forces. We had also derived the equations below, which gives us the path of the orbit, okay, which give us the path of the particle under a central force. And also we had learned so many things about the aerial velocities. So all the formulas below we had learned. And also we had seen the formula above. What we will learn today is something about an apse. Okay, so what exactly is an apse? Okay, this is only defined for central orbits. So if you see the definition, an apse is a point in a central orbit in which the radius vector drawn from the center of force to the moving particle has a maximum or minimum value. So what that is saying, okay, suppose if this one is the center of force, okay, and suppose a particle is moving in an elliptical orbit like this. Okay, it can be any shape, but let us just take it to be elliptical. And if this one, it is the force is present over here, okay, and the particle is moving in this way. What it's saying is the point where the point where the point which is at a maximum or minimum distance. Okay, so if the particle is moving, if you notice this point, okay, if you measure the distance from this O, which is the center of force, it is the minimum. Okay, that is, and if you take, okay, maybe OA and OB, okay, so over here what we are saying is that A and B are both apse, okay, because OA, it is the minimum. It is the minimum possible distance for the particle to be from O. And also B, it is the maximum distance for the particle to be from O. Okay, if you take any other point, okay, it is not the maximum or minimum. So I hope that is clear. So over here we are having the apse to be A and B. Okay, so sometimes you can have only one apse, okay, 2 or 3, okay, depending. So that is what we have defined over here. An apse is a point in central orbit where r is maximum. So over here r is indeed maximum, this radius, or r is minimum. Okay, so whether r is maximum or minimum, then that corresponding point will be apse. And over here you notice that if r is maximum, because u equal 1 by r, then u will be minimum. Okay, so we can even define an apse as a point in a central orbit where u is minimum, or we can define it where u is maximum. Okay, if you notice that an apse behaves as a local maximum or local minimum, okay, so if p r theta is an apse, remember by using derivatives, it is a point of local maximum or minimum whenever du d theta is equal to 0. Okay, how exactly do we know this? Because if you remember that the orbit can be written in terms of u and theta. Okay, so we can think that u depends on theta. So if du d theta is 0, then that point that will be a point of maximum or a point of minimum. So if you have to find an apse, this is the main condition that we will be using, du d theta equal to 0. But also notice that if you put du d theta equal to 0 in the above equation, what will you be having? Which gives, okay, if you put du d theta equal to 0, we will be having 1 by p square equal u square. Okay, but now u, okay, it is the reciprocal. What we are having is 1 by p square equal 1 by r square. P square will be equal to r square. Okay, but we have to be very careful over here. Even though we are writing it as r, it will actually behave as some kind of a constant. Okay, because over here, okay, we can have so many radius. Okay, but you have to be very careful that r has to be taken where it is maximum or minimum. So keep that in mind. All right, So or we can even have P equal R, okay, because both of them are distances. Okay, so after doing this, now we will define some other terms. Okay, so just remember these two things first, at and amps. Okay, these are the things that you really need to remember. Du d theta equal to 0 and P will be equal to R, okay, at the apse. And another thing that we need to define is, okay, number 2, the perihelion. Okay, the point of nearest approach. Number 3, the aphelion. Okay, aphelion, it is the point of farthest approach. So both of them, they are in fact apses. Okay, for example, just like I was saying, okay, if you have this one to be the center of force, then this one, it is the point of nearest approach. So this one will be the perihelion. The perihelion will be A and the aphelion will be B. Okay, you actually pronounce this one as aphelion. Okay, perihelion. And number 4, another thing that we will be learning today is about velocity from infinity. Okay, suppose this is the center of force and a particle is coming from infinity. Okay, how will we describe the velocity? Okay, if this distance is r, what will be the velocity of this particle coming from infinity at this point r? Okay, how will we describe it? Okay, actually you just need to learn the formula for this one. We will do a derivation at some other point of time. Okay, but for now, remember, if a particle is attracted, if a particle at infinity is attracted by a force at O, then the velocity at a distance r from O, okay, suppose the velocity at this point is given by, okay, half v squared equal minus infinity to r f dr. Okay, again, another thing that you will really need to remember. We will do a derivation later, but for now we just need the expression. So with this being said about apses and velocity from infinity, let us just try to see an exercise, okay, maybe involving only apses first, okay, then we will do an exercise involving velocity from infinity another time. Okay, and one thing, whenever you ever try to do these exercises, okay, let me see an exercise from the book. Okay, whenever you see the exercises from over here, from the book or from anywhere, one thing that you need to remember is this, okay, if you differentiate, okay, d theta of d2 du d theta whole thing square plus u square, if you differentiate this one, how much will you get? Okay, keep this in mind. Okay, I will write it down as a note. So if you differentiate it with respect to theta, du d theta whole thing square, you will be having 2 du d theta, okay, and then d theta of du d theta plus d theta of this one will give you 2u du d theta, Okay, so you can take common du d theta. In fact, 2 du d theta, you can take it as common. You will be left with this term d2 u d theta square plus u. Okay, so keep this in mind. Okay, when exactly are we going to use this? Okay, just take a look at equation 1. Okay, you are saying d2u d theta square plus u. So actually in equation 1, what we will do most of the times is we will multiply by 2 du d theta. So once we multiply by 2 du d theta, we will actually transform this one into something that looks like this. Okay, so keep in mind. Okay, equation 1, you will always have to multiply by 2 du d theta.